Okay, guys. Hope you had a good weekend. We need to turn in the group lab report. Got that time. Could you please pass those to the center?
Do you want to write anything on the back?
I think yes. Anybody ready to turn in their group lab report?
You said to run our names on the back as well.
Everything is just like any lab report.
Just write them all, I think. Or either our last, just our last name.
Okay, guys, let's look at the we left off looking at direct, well, we did direct alkylation, and then we were doing indirect alkylation. Indirect alkylation, we can essentially we can add a dummy group to our compound. And that would allow us to use a weaker base for the alkylation. The dummy group will typically be an ester. The ester, once we do our alkylation, the ester can be removed by hydrolysis. You can hydrolyze the ester, and then we can do decarboxylation. We showed the acid, it'd be called a beta-keto acid. Beta-keto acids are readily decarboxylated. You see that a lot in biochemistry. We can look at this decarboxylation mechanism a little bit closer. Let me redraw the beta-keto acid. I'm going to draw it in a certain conformation. Now remember conformations? I mean, this is a conformation, that's a conformation, that, you know. Which is most stable? Well, for me, this is most stable. Because I don't want to stand around like this all day. So we can draw different, we have bond rotation. All right. Of course you do. Beta-keto acid, but let's draw it like, and I may not have, we can raise that up. We got the, let's see, let's draw this like this. There's the beta-keto acid. But I drew it with the H up here. Let's look at sort of two mechanistic pathways. You often see this shown as a transition state. Here. We can sort of say these electrons are going to end up bonding with the H. A nice 1, 2, 3, 4, 5, 6-membered ring transition state bonding. These electrons can come here. These electrons have to go somewhere. They're going to come here. Then one of these pi bonds is going to move up. I'm showing the, we already hydrolyzed the ester. First step is to hydrolyze the ester, just like test 3 chemistry. Once you get to the acid, then it's the acid that loses CO2. And that's called decarboxylation. What does all this electron movement give? What's between this carbon and this carbon though? Double bond. How many bonds now between carbon and O?
Single.
Yes, electrons moved up. How many lone pairs on oxygen? One of them reacted with the H. There's one there remaining with what? See, that became lone pairs. So now there's two there. Now this is bonded to what? H. Okay. Is this carbon still bonded to that carbon? No, the sigma electrons broke away and came over here. Okay. What are we forming right here when this comes down?
CO2.
Yes, there's your CO2. And so we have, I'll draw in the carbon, but now we have double bond up. Of course, it's now linear. Where there it was trigonal planar. There you go. Okay? It's just cyclic. You know, you can draw a transition state where that's breaking, forming, you know. I don't often draw transition states. Again, but you'll see those in textbook. There we go. There's our products. Except this is in what form? That's actually enol form when we do that. And what do we know about enol forms? It will do what? Yes, this will tautomerize. Hopefully you can draw the keto tautomer. The double bond will be here. The H will relocate here. And there you go. And you know the mechanism for the tautomerization. And that's an equilibrium. Which is favored, enol or keto? Keto is highly favored unless there's something that makes this more favored. In this case, there's nothing. We talked about a couple of reasons why the enol might be favored. So, all this takes is a little heat. Okay? So you do the hydrolysis, but you also have heat. And so as soon as you hydrolyze the acid, this will take place. What drives this? One molecule breaking into two. So it's driven by entropy. You see lots of decarboxylations in biochemistry. And again, if you got a when do you get easy decarboxylation? Whenever you have a carbonyl beta to the carboxylic acid. There's your carboxylic acid, alpha, beta. Because that allows you to then do this nice here. Okay? So that's one way to look at the decarboxylation. Another way is more under basic conditions. I'm going to go ahead and show it now. That's acidic. Under basic conditions, what would we have here? I'm going to redraw it and maybe erase some here. We would have boom, boom, boom. I'm not going to really draw it like that. That would be, under basic conditions, wouldn't that be in the basic form? Okay, I'm going to erase here. You could also have decarboxylation under basic conditions. One way to think about mechanism here is, what do we need to do to get CO2? Well, if this moves in, make pi bond, and kick this off. Let's do that, and then let's look back and say, hey, is this reasonable? Boom, boom, boom. What is now on this carbon after that electron movement? Lone pair minus charge. Plus what? Plus CO2. Have we ever said this? Anytime you make a pi bond kick off a leaving group, that's fairly easy to do. Can't kick off a plain carbon. Is this just a plain carbon, or does it have some type of stability? That's an enolate. It has some stability. So another way to look at this is, actually the enolate just kind of served as a leaving group. So that carbanion has some stability. That's not just a plain carbanion. It's a resonance stabilized carbanion. And so again, with a little heat, so there's a couple of ways to look at why these things decarboxylate. Questions about decarboxylation? Now, of course, I mean, our basic condition, if you're around water, now this can exist in water. But as soon as this forms and you got water, it's going to protonate. Because, of course, you know pKa's. And, I mean, this is 16. you would go to the neutral form, which have a pK of 20, and 20 would be favored. So you say, hey, if this is around water, it's going to protonate, where this you would not. Questions? What's the product down here? If we heat this compound, what might you expect? And if you just heat something, you can call that a thermolysis reaction. Well, not if you just heat it. If you heat it and it breaks apart, because lysis. So we're thermolysing it. We're heating and breaking it apart. We're not hydrolyzing it, we're thermolysing it. Thermolysis reaction. Big hint, we're sort of under the decarboxylation topic. What decarboxylates? Carboxylic acids, the CO2 from the carboxylic acid. You got two carboxylic acids. Which one are you going to lose by via losing CO2?
What's the one?
The one with the carbonyl beta?
No.
Alpha beta. Does this one have a carbonyl beta? No. Alpha beta. Ooh, that one does. Okay, this will lose CO2. What will be the product? If you heat this thing, it's going to pretty darn likely lose CO2. And the product will be boom, 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 boom. What do we got here? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5. Right there. Where essentially there's an H here now, or an extra H. There's two H's there. The carboxylic acid on the end is not going to be easily decarboxylated. And basically in this class it will not. So, we lose CO2 here. You can do it under acidic conditions, you can do it under basic conditions, you can also just kind of heat it, and it will, I mean the first where we did the transition state, that really doesn't have to be under acidic or basic conditions. You just draw it so this H is sitting up here, it takes the H. What was this indirect called up here? It was called the acetoacetic ester synthesis. Because if that's an H under my hand over here, that's acetic acid. So that's an ester of acetic acid. And it's like it's acetic, but it also has an aceto. So it's acetoacetic acid, but it's the ester of acetoacetic acid. So that's where that comes from. That's kind of what we're starting with. It's a beta keto ester. I've already mentioned this, but just show it again. Down here, this is a beta keto acid. It's called acetoacetic acid. Acetic acid with an aceto, kind of an aceto group. Or an acetyl. Commonly seen in biochem. And for example, during ketoacidosis, conditions seen in diabetics, where the blood can become overly acidic as a result of the disease. That's because something like this, acetoacetic acid, is formed a good bit. It's an acid. But why is it called ketoacidosis? Because not only is it an acid, but it's a keto acid. It's a beta keto acid. Okay, there's a variety of variations on the indirect. This guy has two esters instead of ester ketone. The same type of chemistry though. We treat this with base, where are we going to make anion at? Well, right here we got this acidic methylene, activated methylene. Why did we use methoxide? Because we have methyl esters, and if the O-methyl attacks the carbonyl and kicks that off, well, no big deal. It's the same thing. Then, once we get our anion formed, we can do the alkylation, and we can get this product. Now, if you hydrolyze this with heat, you'll eventually get that compound, but what will you get first? You'll first get the diacid, because aqueous acid will hydrolyze your esters to the carboxylic acid. In this case, you have two esters. This would be called a beta dicarboxylic acid. If you get rid of the benzyl, that's malonic acid. Malonic acid is a diacid. And this is called sort of the diester of malonic acid, or called malonic ester. In this name, this is not what you're making, but this is what you're starting with. Okay. Either acid you look at, let's call this the main acid. Does it have a carbonyl beta? Alpha, beta. Yeah, carbonyl beta. The carbonyl beta does not have to be a ketone. It doesn't have to be any precise functional group. It just has to be a carbonyl. So this will lose CO2, and when it does, what do you get? You get the product shown. So in these two examples, it's pretty much the same thing, except here you have two esters, where in the previous example you had an ester and a ketone. Now you're not going to lose the ketone. So in the previous example, we knew which acid we were going to lose. Here, you have two acids to lose, and because it's symmetrical, it doesn't matter which one you lose. You know, this could be the ketone for this acid, or the carbonyl for this acid, or that could be the carbonyl for this acid. You lose either one, you're going to get that product. Okay. So, that's indirect. Any questions about indirect? Maybe real quick, let's look at it a little bit different approach. Let's take this compound here and let's convert it to let's say you wanted to do this chemistry where we're adding what to that compound? How many carbons? Adding that. How would you do this directly? You treat this first with what? LDA. And then you'd come back with what? Like propyl iodide. Propyl group with a leaving group. Right? LDA would do what? Make anion here? Is it going to make anion on this side? No. Make anion, and then anion attacks carbon, kicks off iodine. That's how you get your bond made by SM2. Okay, how would you do this indirectly? instead of starting with this, we would start with what? What would we want to have added to this? The dummy group. What's the dummy group? Anisha? Ester, right? Okay. Now we can treat this. We want to put a propyl on this carbon. Isn't that what we want? Isn't that what we did? Well, we can put a propyl here, but now do we have to use LDA to get our anion? No. What base do you want to use? Yeah. Make that. That'll give us the anion. Now we come back with propyl iodide or bromide, and now this will alkylate. That would give that, right? Okay. Can we now convert that to this? Yes. What do you want to use, T?
Acid.
H3O plus and heat. This will hydrolyze the ester to the acid. Then it will be a beta keto acid. Then what will happen to the acid group? You'll lose it. You'll essentially get an H here. And when you get an H there, what do you have? You have that. So you'll hydrolyze your dummy group, and then you'll lose it by CO2 because it's next door to the, okay? So instead, you would start with this. Now, we haven't really said how you would go from here to here. We can do that, but I don't want to get into that right now. But you would start instead with a dummy group on your starting material. This is indirect. Make sense? Okay. Roman numeral 2. Ah, that makes me wonder what Roman numeral 1 was. What's Roman numeral 1? Is it alkylation?
Direct alkylation.
Where is Roman numeral 1? Alpha substitution reaction. Okay. All right. Alpha condensation reactions. 1 and 2 are not clearly distinguishable, but I think really Roman numeral 2 is really sort of a subset of Roman numeral 1. But specifically in Roman numeral 2, we're going to produce something. Condensation.
Water.
We're going to produce water. Okay. Main reaction here is called an Aldol reaction. One of the top 10 reactions in organic chemistry. Let's look at it. In this example, we have a ketone. If you treat it with a catalytic amount of standard base, hydroxide base, it can actually be even weaker base than that. You can actually use weaker bases like triethylamine. And I'll only take a catalyst. We can get this product. Now this comes from 2 equivalents of this. Okay? Of course, if that didn't say that, you would have to say, where did all these carbons come from? And you'd have to realize, hey, it's reacting with itself. Okay? That's why I call it dimerization in this particular example. What type of product are we making?
Alkene.
Alpha, beta, unsaturated. There's a ketone, alpha, beta, unsaturated. Remember we made these before by another way. And we said how important these are. Your aldol reaction gives an alpha, beta, unsaturated. Now the other way, we had a halogen and we just did elimination to put the double bond in. Getting from the aldol is more complex because it involves two large molecules coming together and you get the end product all from the reaction. It's not as simplistic as the first way we saw. Okay. What's going on here? We can sort of hone in on this here and say what happened here, what happened here. Or we can come over here and just do mechanism. What could happen? What could base do to this?
Extract hydrogen.
Yes, we can get anion form here. I'm not going to do mechanism for making that anion. Base subtracts H, make enolate, right? Okay. So I'm approaching this. What could happen?
Low pair attacks the carbonyl on the second equivalent.
Yes, what happens is, I'm going to draw the other ingot just as phenyl. What happens is, one carbanion attacks the carbonyl of another molecule. So these electrons just add to the carbonyl, electrons up.
The second molecule has an anion on the end as well, right?
Well, no, not really. If we look at this here, this is hydroxide. No, I skipped that.
It's water.
What's the pK of our starting acid? 20. Whenever hydroxide removes H, what are we making? We make this plus what? Water. So plus. So we go from 20 to 16. Which is favored, 20 or 16? 20. See, the original non-deprotonated is going to be your major species by 10 to the 4. 10 to the 4 is what? 10,000? I think. Or maybe I don't think. So really, Larry, out of 10,000, only one of them is anion. The other 9,999 are actually neutral. So you got to remember your equilibrium there. Again, also, does hydroxide completely convert this to anion? No, that's why we had to use LDA if we wanted to do complete conversion to anion, right? Okay. So this can attack that. What does that give? I'll draw one ring out. So this carbon is now bonded to carbonyl. Let's draw in that so we can keep track of the carbonyl. Electrons over to oxygen. Is that what happened? What else is on the carbonyl carbon? Phenyl and a methyl. So we just made that bond and we moved the electrons on to oxygen. Does that look right? Okay. Let's see, this has 2 oxygens, our product only has 1. What oxygen is going to be lost? Well, this oxygen is going to eventually be lost. Is O- a good leaving group? No. We're going to need to do an H plus transfer. Where can an H come from? There's 2 places H can come from. You can take it from the water that was formed when the base took this H, and there's also probably some water in your reaction. And I reckon I'll do that. I'll take the H from there. So this takes an H from water, And that's going to give,
NaOH reform.
yes, it will reform NaOH. Boom, boom. Phenyl, methyl, and what's here now? OH. Yes, plus hydroxide. So our catalyst is reformed. So we see how we can get to this place just by using hydroxide catalyst and reform it. Now, this is a neutral molecule. Sometimes this can be isolated. In my reaction, we're not isolating this. Now, where does the name aldol come from? Sort of comes from right here, except we didn't start with an aldehyde. Pretend this is an aldehyde. If this was an aldehyde, we now have made an alcohol. And if you combine aldehyde and alcohol, you can shorten that to what? Aldol. Okay? So this is the aldol product. And we're going to have to clarify that. Because sometimes, a lot of times people call this the aldol product. But that is an aldol because now it has the alcohol. Now, these things will readily lose water. And we can put the double bond in here. Let's do a mechanism. We're under acid or basic conditions? Basic. So we're going to make anion. Okay? I'll do it stepwise. We have that base catalyst. You take the H. And this will give that plus water. Everybody agree? We just made enolate. Of course, this is favored, so equilibrium here would look like that, right? It doesn't mean we can't make some enolate. At this point, we have lone pair. Anytime you can make a pi bond and kick off a leaving group, that's easy to do. What does this electron movement give? It gives double bond between here and this carbon has a phenyl and a methyl. Okay? Plus what? What was the leaving group? Yes. We've reformed our catalyst again. Remember, you would never have hydroxide be a leaving group in an SN2, E2, or any of that. This is where you're making a pi bond with a lone pair, like we've always said. Much easier to do. Anything can leave. Have you ever seen it be a minus? It can leave. Have you ever seen OH be minus? Sure, all the time. Now from here to here, we actually, there's the water we made. So we lost water along the way. And that's why it's called condensation. Because the water is condensed out. And in some cases, in practice, you can actually see it coming out. So this is called the aldol condensation product. Basically, you have to clarify, when someone says draw the aldol product, you're kind of like, well, do you want me to draw this here, which is where the aldol name came from? Or do you want me to draw the condensation product where it loses water. The aldol condensation is an alpha beta unsaturated carbonyl. For us, to sort of give it some clarity, always go dehydrate. Okay? But at the same time, don't be totally shocked if you see something like this shown as a final product, like on an MCAT or something. Because you never know who, what, where how they're gonna show it. So yeah, you just take. By the way, what is the name of this compound? Acetophenone. You take acetophenone and add a little drop of like KOH, a little ethanol. Shake it for a couple hours. You'll have this product here. Now, how fast does this lose the water? It can sometimes depend on how stable your double bond is. And that can be based on conjugation. You see this conjugation? I mean, there's extensive conjugation all through here. This double bond is going to want to be put in.
So by removing the water, you can drive the product to the...
Well, you actually don't have to. You don't have to remove any water here. It's thermodynamically driven because it's so conjugated. If that was not a aromatic ring, it may be a little more difficult. Okay, that's symmetrical aldol. Before we go on, let's look at the product here. Whenever you're looking at this stuff, you got to come at it 500 different ways. Okay? Like backwards. How would you make this? How can you break this apart? What we need to look at is, we essentially made an alkene here. Right? Wouldn't you break this apart right here? You got the ring and 2 carbons on that side, you got the ring and 2 carbons on that side. What was each carbon originally? One was one thing and one was another. One of the carbons was a carbonyl. Let's label this as A and B. Which one was originally a carbonyl?
B.
Yes, that's B. Originally a carbonyl. What was A originally? An alpha carbon. Or we could say it was the enolate carbon. Whenever you do an aldol and you get your double bond, one was originally an enolate carbon, the other was a carbonyl. Because this chemistry involves the enolate carbon attacking the carbonyl, and then you lose water to put in the double bond between them. Okay? Now, pretend you had a brand new reaction, all you had was the product. Can you look at it and tell me, of A and B, which was the alpha carbon? Which one was the alpha carbon? How do you know A was the alpha carbon? Because it's an extra carbonyl. Okay, the alpha carbon is still next to the carbonyl. Because the carbonyl of the enolate, nothing happens to it. Okay? What I'm trying to get you to do is to look at a final product and say, hey, I can make that by an aldol. This carbon would be the enolate, that would be the carbonyl. See, the carbonyl B, that oxygen is now gone. That used to be double bonded in. Okay? Now, let's look at the bottom, but don't look at it except for what I tell you to look at. Alright? Look at the bottom, but only look at the top right compound. There it is, right here. No, I'm sorry. Let's do one that's a little bit different. Look at the right bottom. Over here. Got right there. See that one? Don't look at anything but that. Far right bottom. Now this comes from a non-symmetrical. No, actually, I'm sorry, it comes from a symmetrical. This is just like what we did. It's a symmetrical product. Can you show the starting material that would give that by a symmetrical aldol? First off, it's an alpha beta unsaturated carbonyl compound, right? These come from aldol reactions more often than not. Okay. Of the two carbons, the alkene A and B, which one was originally the enolate carbon? A. And what was B originally? Carbonyl. And we break that apart. Make that an enolate carbon. Now, how many H's do we put on that carbon? Do we need to put another methyl or anything else, or what is there as H's? Yeah, we don't like to start adding more alkyl groups. And what's the bottom going to look like? B, boom, boom. But this is B is double bonded to what? Oxygen. And what else is on B? It's not drawn. H. And you see how those are the same thing. This comes from two of these same molecules reacting. You treat this with a little base, what happens? You get a little anion formed. Then it attacks that. You should do your mechanism how you eventually get there.
Isn't that polymerized?
You call it dimerization. It's just two molecules reacting.
It won't do more than two.
Yeah. We could do additional chemistry that we're going to learn next. Possibly we could get trimer. But this is typically dimer. Where polymer sort of suggests it's like millions of molecules coming together. Okay, let's do one that's non-symmetrical. Okay? Again, don't look at everything down there. How about the one up above? Can you break that apart into, when you do an aldol, it's an aldehyde ketone, self-reacting, or we could have one aldehyde or ketone reacting with a different aldehyde or ketone. That would be a non-symmetrical aldol. And that's what this comes from, because obviously there's only one phenyl, and the other molecule didn't have a phenyl. Can you break that compound into, up here, into starting materials for an aldol? Well, let's do it. It's an alpha beta unsaturated carbonyl. We can make the double bond by an aldol. Of the two carbons, A and B, which one was enolate or alpha carbon? A. And it's just one carbon, right? That implies that the rest here is going to be H's, and there's actually 3 H's there. Now the other portion, B, was what? Yeah, it's actually this guy over here that we've already drawn. Yes, this would come from reacting this with this, where this is the minus, and it dehydrates onto the carbonyl. How do you lose water? 2 H's are lost from here, and you lose the oxygen. That's where your water comes from. And when you lose 2 H's there, there's only one left on A. Okay? You should be able to break these apart. Now let's look at it starting fresh. Okay. That was symmetrical aldol. You can also do a non-symmetrical. Those are also called mixed aldols. 2 different components. For example, you could react this with this. The problem with a mixed aldol is selectivity. You're going to get 4 possible products. For example, where are you going to make enolate? You can make enolate there, but you could also make enolate where? Right there. Now this enolate could react with itself. Now not actually itself, but another molecule of its same kind. And if this reacted with another molecule of the same kind, which product would you get?
The top.
You could actually get that. Now if this enolate reacted with that carbonyl, which one would you get? You would get that one. What over here? What if this enolate formed and reacted with itself? Which one would you get?
Right.
That one. What if this enolate reacted with this carbonyl? You get that one. Now which one's going to be favored? Now you could make an argument based on which one has more stability, but in this case it's going to be a mess. This is not going to be a selective reaction. See, back up there was no alternative. That's the only product you could theorize from an aldol. It's 4 possible products. It's going to be a mixture. But hopefully you see how these are put together. Okay. But you can do mixed aldols and get good products. You have to have a reason for selectivity. For example, this reaction, you get a good product. Let's see why. First off, if you treat this with base, where are you going to make carbanion in? Right there. Can you make carbanion here?
No.
The aldehyde H is not acidic. There's no alpha carbon with an H. So there's only one place to make carbanion. So instead of 4 possible products, we only have how many possible products? 2. There's 2 possible. So we cut our possible products in half. What are the possible products? This could react with another molecule of itself, or that could react with that. So we cut it down to only 2, because we cut the number of enolates in half. Now, obviously that product comes from this reacting with what? With that, because if you cut this in half, that's enolate. What does that carbon used to be? Carbonyl with an H, it's actually that. So why that? Why does that not react with another of itself? This sort of comes back to, well, which one's more electrophilic, the aldehyde or the ketone? That should have been quick. This has a methyl donating. Which carbonyl has more positive? Aldehyde. Aldehydes are more electrophilic. So as soon as you get some carbanion, it's going to go straight for the more electrophilic carbonyl. Not only because this has induction, but also because the methyl adds sterics, which is more difficult to attack. So that's the argument of why you get this product and not its self-reacting. And indeed, if you do this reaction, you get good yields of that product right there. So we have some reason for selectivity. Where
You would think this, but it wouldn't be the only one. You would get some of the other.
theoretically you would. In practice, you get a great yield of that compound shell. There's often a difference between, theoretically, but you can make this a 90% yield. But there is a dimerization product that you can theorize, where this self-reacts. Okay, recall, we made a very similar product from here, right? By how? By halogenating and then eliminating? We already did that. Okay. There's actually in one of the packets that has lots of miscellaneous sort of handouts in it. There's an Aldol reaction in there that came from an ad in a magazine. And it shows multiple Aldol products. But actually one of them is incorrect. Their national ad has an incorrect product in it. Take a look at that. But also please look at this. These Aldol reactions you can also do them intramolecularly. Okay? Take something like this, we can make rings. Please be looking at this and think about what size rings are best. Okay guys, we're checking out in lab this week and you're turning in your notebook pages from the recycling. So have a good week guys.